Okay, fine.
Okay, so first of all, I would like to thank Professor Senthil Velan for the very kind introduction and for having me here. Yeah, I think he first invited me in 2014 or 16 maybe, and I've been trying to come, but with various reasons it hasn't happened. And really glad to have come here. Uh, so actually, I visited this university maybe 25 years back, and as a student. And it was a great school that was organized here, I think, by Professor Lakshmanan. Uh, so it's nice to be back. So I think Professor Senthil, he asked me to say a few words about ICTS before I start. So ICTS, as you say, International Center for Theoretical Sciences. So it's now about maybe 12 years old institute. It's a center of Tata Institute of Fundamental Research, which is in Bombay. So this is a center in Bangalore, and it has three sort of different objectives. This center, one is of course just research, and there are various areas in research that you can, if you go to our website, you will see there are high energy physics, string theory mostly, and complex systems, which is statistical physics and condensed matter, astrophysics, and mathematics. So roughly these are the areas of research. And apart from research, one sort of important objective of ICTS is to organize programs, which includes conferences, schools, and workshops all throughout the year. Okay, so if you go to our website, you will see that there are conferences or schools and various things going on all through the year. So you are encouraged to look at those, and if anything is useful, you should apply. And yes. We also are very strongly involved in outreach activities. That's one of our mandates. Okay, so yeah, so you can, if you go to our website, you will get a lot of information. And the school that I organize is a school on statistical physics with my colleague Sanjeev Savapandit at Raman Research Institute. And we have it every year. This year also it's going to happen. We have will announce it soon. Uh, it's usually on slightly advanced topics, but maybe some of you will find something interesting. Okay, so today I'll talk about this. Yeah, so you mentioned that I'm very punctual with timings, but today is it exactly 1 hour, or
No.
I can go a bit flexible, right? Yeah. So please ask questions in case if you want to ask, because at least some part of it you should be able to understand completely. So I hope please feel free to ask any questions. So the basic idea of this problem that we are looking at is there are, if you take any in like physics problem, usually there are two ways of describing it. For example, the air in the room, you can of course look at the molecules and atoms at a microscopic level, and then there is a hydrodynamic description. Okay, so you just treat it as a fluid which has a velocity and the density and so on, pressure and so on. So there are just two ways of describing this, and are these completely equivalent? Okay, so that is the main question. So I'll try to explain this. And we try to test whether this is really true. So this is work done with a postdoctoral fellow at ICTS, Shubhadeep Chakraborty, a student, a PhD student of mine, Santosh Kannappa, and a colleague at Boston University, Paul Krapinski, and it has appeared in this paper. Okay, so let's look at this question of what are the microscopic laws in physics. So if you look at a box filled with, let's say, water, then if you look at closely, what we'll find, of course, with the microscope, if you see, then you'll find that it is made up of molecules. And yeah, these molecules, if you are just thinking of the classical description of classical physics, then the molecules basically satisfy Newton's equation, right? So you have n molecules, I equal to 1 to n, and each molecule has some position and momenta, and this is just Newton's equation. Mass into acceleration into force is equal to force. Okay, and equivalently, this sort of Newtonian equations can be written in the form of Hamiltonian dynamics, where you have some Hamiltonian function which has kinetic energy plus potential energy, And then the equations of the second order differential equations can be written as a set of 2n first order differential equations. The rate of change of position equal to del x by del t, this is as momentum, and the pi dt equals to gradient of the potential. So this is Hamiltonian dynamics. So so you have a set of n equations for these n atoms, and if you know the initial conditions like position and velocities of all the particles, then you know exactly what the atoms are doing. Okay, so this is the microscopic picture. But of course, we in our real life we can't see the molecules, right? So what you can typically measure is something like you can put a barometer or something and measure the pressure. You can put a thermometer and measure the temperature of this room, and you can find the density of air in this room and so on. Okay. So these are the things you can measure, and then we know that there are these macroscopic laws. For example, thermodynamics, which tells us a lot of things about this observable quantities. So there's the first law of thermodynamics, second law of thermodynamics, and then there are things called equations of state, which tell us that this pressure is related to temperature and density in a particular way, right? So P equal to rho into T for an ideal gas. So if you know one of the things, you know the other third quantity. So similarly, you have so the other things that you can measure are things like specific heat, compressibility, and so on. And all these are all sort of measurable quantities which thermodynamics tells us how to compute. So now, so this is all equilibrium physics, and there's a beautiful connection between these macroscopic laws and microscopic laws, which is basically given by equilibrium statistical physics. Okay. So, I mean, what equilibrium statistical physics tells us is that, like, if you have air in this room, then you don't need to really care about all the molecules, about the individual molecules are doing. If you know the total number of molecules, the total volume of this room, the total energy of all the molecules, and the total momentum, then there is, and you know the Hamiltonian, okay, at the microscopic level, you just know the Hamiltonian. So Hamiltonian is a function of all the microscopic degrees of freedom. And so at the microscopic level, what you know is that, so the Hamiltonian, it's basically the energy. And in this big, there's a 6n dimensional phase space on which in which this the system is moving, the microscopic system. So because energy is a conserved quantity, it moves on this energy surface, and you can ask what is the area of this energy surface. Okay, so if you compute the area of this energy surface, let's call it omega. So I've written it in some way. Then once you compute this, and then you take the log of this quantity, and this is Boltzmann's constant. So kb log omega. This depends just on these constants: energy, volume, and number of particles. Okay, so you find the entropy in this particular way. So I hope this is clear, right? I mean, so I mean, let me just say, even if you have a single oscillator, so let's say even if you have a single harmonic oscillator, the Hamiltonian is given by p square by 2 plus omega square x square by 2. Mass is 1, let's say. So this means that in phase space, so this is a two-dimensional phase space. You have some ellipse, and supposing you find the area of this ellipse. Okay, so that is what I called omega. So this corresponds to a particular value of this Hamiltonian function. So this E omega will be a function of E, in general, the number of particles and maybe the volume of the system. So you just have to calculate. So this is the microscopic picture. You have the Hamiltonian and you have phase space. You compute the area of this constant energy surface, and then you just compute this function, and then this function contains all information about the equilibrium properties of the system. Okay. So this is quite an amazing thing. From this, once you compute this function, you can find the equation of state. You can compute the specific heat of the system, compressibility, everything. So all equilibrium properties are completely determined by this single function. So this is the achievement of Boltzmann and Gibbs, and this is what gives us this equilibrium statistical physics. Okay, so now supposing we look at non-equilibrium systems, then things get a bit more difficult. So out of equilibrium systems are like if this I mean air in this room starts moving, or let's say you take a pipe and there's water flowing through the pipe. That's a typical non-equilibrium system, or water boiling in a beaker, or a cyclone, or let's say supernova explosion. Right? These are all out of equilibrium systems. So in this case, I mean, how do we go from the microscopic to macroscopic picture? Okay. So there the idea is there's this idea of local equilibrium. So what you do is imagine this is a pipe through which let's say air is flowing, and you can of course look at molecules inside, and they are just following Newton's equations or whatever. But now supposing you look at you no, so this idea of local equilibrium is that now because things are flowing, it might be that if you measure the temperature here or measure temperature here, it's different. Okay. So what you think of is that you think of this divide this cell, this entire system into small cells of let's say some size L, capital this small L. So the small L is small if I compare to the size of the room or the size of the pipe, but it still contains thousands of molecules. Okay, and then what we say is that within each such box, the system is almost in equilibrium. Okay, and then if it is in equilibrium, then we learned from this previous thing that equilibrium is described by these quantities. Okay, so these quantities are important because they are conserved quantities. Okay. That's there. Okay. So see this. What is special about these variables? So the number of particles in the room is conserved, the energy is conserved, volume is of course conserved, and total momentum is conserved. Okay. So in general, if you have Hamiltonian system, maybe you have heard of systems called integrable systems, which have a large number of constants of motion. But most dynamical systems they have very few constants of motion. Okay. So, and somehow these constants of motion are important for a macroscopic description of a system. So, in this case, the same variables that I used in the equilibrium case, I use the same variables, but now they depend locally, they change with space and time. Okay. So this number of particles in this small box, total amount of momentum in this small box, and total energy in this small box, if I find, then this will give me a local description of the equilibrium state in this small box. Okay, and then this of course will change as I go along the is this pipe. So in each small box, I have some local equilibrium, and here I can write equations of state and so on. But these things are changing with both space and time. Okay, and the question is how do they change? Okay, so this is one idea because these are conserved fields, they evolve slowly, and their evolution is given by the equations of hydrodynamics. Okay, so this is the important idea. So when you go from equilibrium physics to non-equilibrium physics, in non-equilibrium physics you still have the same fields, but now these fields vary slowly in space and time. Okay. Okay, so basically, what one can do is one can construct these three fields. So now I go to this field description. This is the density of particles, which is depends on space and time. So I'll do everything in one dimension just for illustration. In principle, you can do it in any dimension. So x is the space degrees of freedom, and t is time. And this density rho is just I count the total number of molecules in this box and divide by length L. That gives me the density field, which I can in principle write it in this way. Okay, so this is a delta function. This is the position of the jth particle, and this delta function just counts it. Is it at position x or not? So I sum over all particles, and there's this mass of each particle. So this gives me the density at point x. Okay. So similarly, I can find the momentum density at point x and the energy density at point x. From this momentum density, usually one can define a velocity field. So velocity field is just defined as density field times velocity field gives the momentum density. Okay, so basically starting from microscopic variables, for any microscopic configuration where I know all the positions and momentum of the particles, I can find these three fields which will give me a coarse-grained description of the system, right? So just imagine in this room, I can just measure, of course, density of air at different positions. And what I'll find right now, if I measure the density here, I'll find that it's changing all the time, right? Because air is flowing, there's temperature gradients, everything. So this is varying all the time. So that is this quantity. Similarly, I can construct all these three things in this room, and I want to study how they change with space and time. So now, what are the equations for these objects, these coarse-grained variables? For this QIPI, I know that the Newton's equations are the equations of motion. Now, what are the equations for these coarse-grained variables? Okay, so these are the equations of hydrodynamics, and these equations were written by Euler and Navier-Stokes in the, I think maybe in 18th or 19th century. And when they wrote, of course, they wrote it completely phenomenologically. Okay, so they didn't derive it from microscopics. They just wrote these equations purely from intuition. Okay, uh, so this first equation, so all these equations are the equations for these three fields: rho, velocity field, and energy field, and and basically they all have the form of continuity equation. So basically, if you have a conserved quantity, then you know that it has to have some form like this is a continuity equation, right? Del rho del t plus divergence of some current equal to 0. Now all these equations have exactly this form. So this is density and this is a density current, rho times the velocity. So this is the usual continuity equation one knows. Then for momentum, similarly one finds that this is the momentum current, and then there is some other terms here. So this is because of viscosity. Okay, so if you're in a fluid, I mean you have viscous forces. So you have these additional terms, and this is the energy continuity equation. So there's an energy current which has these terms plus some dissipation, and this thermal conduction. So thermal conduction is just kappa times Fourier's law. So do people know Fourier's law of heat conduction? Uh, I mean, how many people know Fourier's law of heat conduction? Uh, we know. So it's basically, if you take a pipe and if you put different temperatures at two ends, then there's a heat current, right? And so you can measure the temperature everywhere. You'll find a temperature gradient, and the heat current is given by what? Some kappa times gradient of temperature. That is Fourier's law, and so I am using that law here to write this equation. So because this is conservation of energy, so the heat conduction comes here. Okay, so basically in this equation you have viscosity, thermal conductivity, and then there are these other terms. So these black terms are, if I drop these red terms, that's called an Euler equation, and with the red terms it's called Navier-Stokes equation. Okay. So I mean Navier-Stokes equation, normally if you want to study flow of water through a pipe, you'll study Navier-Stokes equation. And that is exactly, but I'm just writing it in one dimension, so it looks maybe a bit simpler. But this is exactly the equation that you write for water flowing through a pipe. Okay, so now to solve these equations, I mean, so basically it's a set of partial differential equations for three fields, rho, u, and let's say this epsilon, which is the energy density. And then you see there are some other terms like pressure. And pressure, one has to use this again, this equation of state. So it's not a new field, it depends on the other fields like density and temperature. And similarly, here this epsilon, this is the energy density. it depends on the internal energy plus the kinetic energy. Okay. So finally, this equation has the three unknown fields and rho, u, and temperature, and there are three equations, partial differential equations. Okay. So this is, I mean, equivalent to the Hamiltonian dynamics for microscopic picture. This is the equivalent macroscopic equations.
So the third equation is written for convenience, the right hand side.
Third equation is
Because written in the conserved form.
yeah. So all of them are in conserved form.
Yeah, suppose the third equation not in conserved form.
So that would happen if you had like external some like driving. If you have water like you are driving, then it would be an external source. But if you just look at an isolated system, then there's no external. So it has everything has to be in this form. Divergence of something. Yeah.
Yes, no?
Yeah. Yeah.
So when you go from your microscopic picture to the macroscopic picture,
Yeah.
you have to, if I'm not wrong, you have to include the collision, right?
Collision is right.
You have
Yeah.
to include collision integral for you to derive this.
Right. Yeah.
How does that? What if you don't take it into account? Will you be able to still get these equations?
No. So if you don't take into collisions are especially important for this dissipation terms. If you don't have collisions, I mean, you can still get the Euler equations. This equations.
If I take Maxwell, Boltzmann distribution for if I substitute it over here, will it still satisfy?
No. So I mean, so from the Boltzmann equation, if you start from the Boltzmann equation, you can almost derive this. But yeah, the collision term in the Boltzmann equation, that will precisely give this dissipation terms, and the other terms, the non-collision terms, will give actually these terms. Okay, so I mean, what he's asking is basically, I mean, if you start from Newton's equations, then from there actually, if you do kinetic theory, then you can derive like Boltzmann equation. Okay, so that is one step between microscopics and hydrodynamics is Boltzmann equation, and then from Boltzmann equation you can derive this after one more step. Okay, so now you have a different set of equations which tells us how fluid in this room will evolve with time. Okay, so now basic question that we wanted to ask is exactly what we were asking: how to derive those equations, right? So when, like I said, when Euler and Navier-Stokes they didn't derive it; they just wrote it. I mean, so that's also quite. Amazing. They wrote actually exactly the correct equations, right? Without just from physical intuition. But deriving this from the Newton's equation is very hard. Okay, so what we want to ask is, okay, so this is the question: is there a rigorous derivation of hydrodynamics from Newton's equation? This was our first question. Now, actually, this is part of famous. So there was this mathematician Hilbert, who had a large set of important problems that people should solve. Problems in maths, but many of them are inspired by physics. And one of these problems is specifically this: how do you go from Newton to Navier-Stokes? So in this aspect, some progress has been made, and one of them is like if you start from kinetic theory, which is again due to Boltzmann, then there is some way to go from Boltzmann to this Navier-Stokes. Okay, so now we basically ask this question: how accurate is the hydrodynamic description, and what are the limits of its applicability? Okay, so supposing we ask this question, like there is a particular problem where you can solve Newton's equation and see what happens, or you can solve this partial differential equations and see what happens, and do they agree? This is the basic question. Okay, so what we'll study is something called a blast wave problem, which is kind of a very extreme situation, okay, and where you might worry that maybe hydrodynamics does not work. I mean, Newton's equation should always work, but because it's everything is very discontinuous and extreme, so there is some worry that this hydrodynamic description might fail. So, that's why we wanted to study this particular problem. Okay. So let me now explain what is this blast wave problem, which is a very interesting old problem. Okay, so this problem was started, I mean, people started thinking about this problem in 1945, around the time of the first atom bomb explosion. So this is a picture of the first test explosion. It's called the Trinity Explosion. And what you see is the effect of the explosion 16 milliseconds after this, after the explosion, after the detonation. So this is about 200 meters high, and then what you see here is like at various times you take the picture of this blast. Okay, so you just image the blast at different times and see how it's spreading. Okay, so so the basic situation is that this explosion creates a region of a very high, very hot region and extreme temperature, and there's a, as you can see, there's a sharp shock front. Okay, so there's a shock region which is obviously expanding in time. Okay, and we want to understand how does this evolve in time. Okay, so this is the situation we want to understand. Just imagine you explode a bomb here. Okay, explode a bomb here, and so it's extremely hot. What is the effect? How does it spread? Okay, so now. So this is a problem where this Von Neumann, G.I. Taylor, and Segov, I mean, all these people were trying to understand this explosion, and there's one quite remarkable result that you can obtain for this problem without doing anything. Okay, so if you ask, well, the first question is, I mean, what is this? There's some size of this blast. Let's say I'll keep this capital R of R. Okay. How does capital R change as a function of time? That's the simplest question you can ask, right? So now what Taylor and Von Neumann, what they said is that what can it depend on? Okay, so it can depend on basically maybe of course the total energy that you release in the blast. Obviously, it should depend on that, and then it depends on the density of the surrounding air. Okay, and then after that, it shouldn't depend on anything else. So they just tried this very simple dimensional analysis. So, so like I said, R depends on total energy of the explosion, the density of the atmosphere around on which the shock is growing, and it depends on time. Okay. So supposing you just try this dimensional analysis, you put e to the power a, rho to the power p, and t to the power c. Then you just equate dimensions on both sides and you get this simple formula. Okay, so here d is that you can do this analysis in any dimension, 1D, 2D, and 3D. So if you do this, you just get this very simple formula.
I have a question.
Yeah.
So you have the variable where the factor where it depends on the ambient air density, right?
Right. Yeah.
Now explosions don't happen also in space. So there you have almost no air.
Oh, you're saying in like a supernova, right?
Exactly.
Yeah.
In that case, that means the blast area should continually expand. It should not stop at all because you're.
Yeah. So even this won't stop. Of course, it will weaken after some
This
time.
will decay. But
Right. Yeah.
if you apply this to a supernova case,
Right. Yeah.
to somewhere where it's in space, you don't have any kind of density. And since it's the denominator,
Yeah.
the radius should, with enough time goes on, it should just keep expanding and expanding. But we don't observe that in.
Right. Yeah. Actually, my next slide is the supernova, so maybe we'll discuss that in the next slide. Right. Yeah. So, but yeah. So for the case of this blast in atmosphere, this is the formula. And so if you put 3 dimension here, which is where the atom bomb exploded, so then you get t to the power 2 by 5 in dimension. So 3 dimension, this is the formula, and this is feed of this formula to the actual data that you see here. Okay. So if you just take this data and see how R grows with time, you find this e to the power 2/5 behavior, and it fits with this line perfectly. Okay, and in fact, you can also estimate, and just from the data, you can now use this formula to estimate the total energy released in this blast. And you get a number which is actually one of the best estimates of how much energy was released in this atom bomb blast. Okay, so this is quite remarkable that such a simple analysis gives you so much information, right? I mean, almost doing nothing. Okay, so this was your question. So this actually this same formula is often used to estimate, like if you have a supernova explosion, and this is a picture of the Crab Nebula. There, it's a very similar situation, right? So suddenly there's a burst, and then it spreads. Okay, how does it grow? And people use this almost the same model to study this. And there's a very nice book called Classical Physics by Branford and Thorne. And chapter 17.6 discusses this problem and the same analysis that I discussed. So yeah, what you are asking is interesting because I mean it looks like rho infinity should be 0, and then how do you apply this formula, right? And right now I can't think, but what I would imagine is that there's always, of course, dust. I mean, it's not complete vacuum, right? There's always dust around the supernova. So I don't know if what they use in this formula is the overall dust density or.
This was an approximation made by Taylor and Horner.
Yeah, they were of course not looking at supernovas, right? They were just analyzing the atomic bomb. So they didn't worry about supernova. But if you look at this book, which actually is a very great book for learning all sorts of classical physics, everything is there. Okay, so you can actually extract very useful information like how this supernova explodes, like the speed of the front and so on from this problem. Okay, so now we want to understand not just how the front is exploding, but also like what is the temperature inside what is the form of the temperature profile, right? Inside the blast, what is the density profile, what is the velocity profile inside the blast? Okay, so these are the other interesting questions. So the only thing right now we know is how R grows with time, but what about these profiles inside the blast? Okay. So what you can do now is we have these Euler equations. So the Euler equations, I remind you, are so initially I wrote the hydrodynamic equations which had some red terms here. Those are called the dissipative terms, including viscosity and thermal conductivity. If I drop those terms, it's called the Euler equations. Okay, so these are obviously simpler equations. So I mean, to understand how this bomb explodes, what these people, Von Neumann, or Taylor and Segoff did is solve these equations in 3 dimensions, starting from an initial conditions where you have like a very high temperature region and then given density and velocity. Velocity is 0, let's say. And so there is some initial condition for the 3 fields, and you just solve these equations. Okay, so now, so to solve these equations, you also need some like equation of state, and this you can just assume that it's an ideal gas equation of state. In reality, of course, it will be more complicated, but this is the simplest assumption that these people. So TVNS refers to Taylor, Von Neumann, and Segoff, who solved the problem first time. Okay. So so even though it looks like very complicated nonlinear equations, quite amazingly you can actually solve them in a particular situation. Okay. So so what they've also found is that I mean, so there's some initial condition where there's in the high temperature and so on. But after a long time, if you look at what is happening, it turns out that the solution is something called a self-similar solution. Okay, so it is independent of initial conditions, and it goes to some particular scaling form. Okay, so what they saw is that so this again follows from some dimensional analysis. Is that the density at position x and time? I mean, it has a simpler form. Okay, so density is a function of x and t, but it takes a particular special form which has this, let's say, it's some function of. So x and t come in a particular combination. Okay, so it's this combination x by t. Similarly, the velocity field x by t, it comes in the combination x by t into some function v of x by ta. Okay, So this variable x by t to the power a, I call it z, and that is this is the scaling variable. Okay, so yeah, so this is what happens at long times. So independent of initial conditions, the solution at long times goes into this particular scaling form. So it's called a self-similar scaling form. And
Dimensions of the scaling?
sorry.
Dimensions of the scaling?
Yeah, so these functions are dimensionless. So that's why I pulled out x by t and x square by t square.
It's dimension.
Right, yeah. So they are dimensionless variables. And okay, so now there is one other important factor, which is that so let's say if I look at the velocity field, I mean the density field. So at time t equal to 0, it was completely flat. After some time, after the blast, if you look at it, it acquires some profile. Maybe at the it becomes something like this, maybe. Okay. Sorry. Okay, so one of the things you notice is that there's a discontinuity at some point. Okay, so there's a distance r of t. Right, clearly. Okay, so if I plot the density as a function of x at time t equal to 0, it looked like completely flat. Then after a long time, if I look at it, okay, it looks like so of course total density is conserved, so it has to be like that. But beyond some point, the gas is unaffected. Okay, so there's a shock front. So this is the distance r of t. So beyond this, nothing is unchanged. But at a particular point, there is a sharp jump. Okay, so that's the shock. So so these are all these solutions have shocks in them, and at the shock there is a discontinuity, and this discontinuity is given by something called a Rankine-Guggenheim boundary condition. So this is not very important. This is just to solve the differential equations. You need some boundary conditions, and this turns out to be the right boundary condition. Okay. So now I take this scaling form and I plug it into this equation. Then of course the partial differential equation becomes ordinary differential equations in for these three fields G, B, and Z. Okay, so now it becomes three coupled ordinary differential equations with some particular boundary conditions. And this is somehow it looks very complicated, but and they were able to find an exact solution. Yeah, so I thought I'll show this because I mean this is a place of nonlinear dynamics where a lot of exact solutions have been obtained, and so this is of course. So basically, what they did is that somehow they made this transformation of variables a into log c, and then you get this three nonlinear equations, and this can be has an explicit sort of solution. So this is the final solution. So final solution means we need this scaling functions g, v, and z, and these are completely determined here. So so this first equation determines v. Of course, it looks you have to invert it numerically, and then z is given in terms of v, and g is also given in terms of v. So you have a complete solution of the equation. So this you can in fact do also in 2 and 3 dimensions, and so this was for 1 dimension. This is what we did in our paper. In higher dimensions, it was already done. So this was a small extension. Okay, so now so far what I have shown is the solution of the hydrodynamic equations. Okay, so now the question is, does this agree with what you will see if you do a direct simulation, molecular dynamics simulation? So this question was asked, so first time, various people have looked at this question, and in particular, there is this person, R. Rajesh in Institute of Mathematical Sciences in Chennai. His group has been looking at this question for a long time, and what they studied is the 2 and 3 dimensional blast problem. Okay. So what is the so numerically what do you study? Like in now the microscopic picture. Okay, so what do you do in the microscopic picture? So in the microscopic picture, what you do is you just do molecular dynamic simulations. Okay, because this is of course a very difficult problem to solve analytically. Like you have million particles. I mean, they are evolving. What do you do? Okay, so here what I show is simulation result where initially you take, I think there are about 1 million small hard disks, okay, placed on a 2D two-dimensional box. Okay, so you can't see all the disks, and all of them initially are at rest. Okay, so this is like our cold gas, and then what you do is at the center, you just excite a few particles, you give them a lot of energy. Okay, so like maybe 5 particles, you just randomly give them a lot of kinetic energy, and then they start evolving. Okay, so initially few particles excited, then they hit the neighbors, and slowly it spreads, right? So now this is a picture after maybe after some amount of time, you find that you have a nice spherical ball of excited particles. So this is the shock front. Right? You can see a front clearly. Outside it's all static. Inside it's very hot. Okay. And here you can see that already there's a density profile inside. Like at the center, there's a very low density. At the side, there's very high density, and so on. Okay. So there's a density profile. If you measure the temperature, you'll find the temperature profile and the velocity profile. And now the question is, from a molecular dynamics simulation, you can compute all these quantities, and then you can compare with what we found from the Euler equation solution. Right? That is the main idea.
So how do this all in molecular dynamics?
So molecular dynamics, you have these hard spheres, right? So you dynamics is much simpler than if you do, for example, differential equations like Runge-Kutta or something. Here, they just evolve between. So between collisions, it's just ballistic. Then they collide, and after collide, they just conserve energy and momentum, and they after there's some new velocity. So it just collide, and then they again evolve ballistically, again collide. So this dynamics can be simulated extremely efficiently. It's event-driven kind of probability. No, it's completely deterministic, right? Because you know exactly what happens after every collision.
All these particles.
Yeah, all particles. So you just have to find when is the next collision, and you keep moving then according to that. So right. So this is much more efficient than if we took, let's say, Leonard Jones or something where you have to do Runge-Kutta or whatever.
Why is this much more efficient? Because you have to calculate for every single particle, you have to calculate its pre-momentum and post-momentum.
Yeah, but
Legally, it costs a lot of computing.
yeah, but it's efficient because between collisions, it's a very easy, simple motion, right? You know exact solution.
Yes.
So between you just evolve. You don't have to do dt. Yeah, it's just one step. They just evolve, and after that again you find when is the next collision, again evolve. So it's called event-driven simulation. So this is much more efficient. Okay, so now, so these people, I mean, they did a lot of comparisons of what, like, between molecular dynamics and hydrodynamics. And surprisingly, what actually the first group that they said that they got very good agreement between hydrodynamics and molecular dynamics. But then Rajesh's group, they found that there is serious disagreement between the two things. So this is when Rajesh came and gave a talk at ICTS, and then I got interested in this problem. So we so we looked at an even simpler problem, which is a one-dimensional gas. Okay, so 3D there are certain problems, and in 1D you can make it even simpler. Okay, so that's why we looked at the 1D one-dimensional gas of hard-point gas particles. So now there are some advantages. So the first advantage is if you want to do a simulation in 3 dimensions or 2 dimensions, you have to take hard disks. Okay, you can't take point particles, because if you take point particles, there are no collisions, and so there's no, not much happens, right? But in 1D, you can really take point particles. There will always be collisions. Okay. And if you take hard disks, the difficulty is that the equation of state is no longer ideal gas. Then you have to, it's a much more complicated equation of state, which is you have to find numerically. So this is why we looked at the 1D case, and again we have of course this exact solution of the TDA in this equation, and it's also easier to do simulation again. So it's again just event-driven simulation. Okay, so we won't discuss this, but okay. So this is the system that we are studying. This is our microscopic model. So you have a 1D line, and you have a bunch of particles which I color red and blue. So this just means that they have different masses. Okay, M1, M2, M1, M2, M1, M2. Okay, the reason I take different masses is that if they are all equal mass, then in one dimension somehow it becomes a very trivial problem. Okay, so if they collide, they have to conserve energy and momentum, which means they just exchange. You have seen, right, like in like this kind of carom thing. If you take a carom and hit it with another carom, it will move with the same, yeah, right? Just velocity exchange. One guy goes to rest and the other goes with exactly the same. But if you make their masses different, then of course when you hit with the big carom striker, this guy will have a less here. So if you do this M1, M2, M1, M2 model, it's a completely different model system. Okay, it's very, I mean, what you can show is that it thermalizes very fast, and it's non-ergodic, it's ergodic and so on. Equal mass is an integrable system. This is a completely non-integrable model. Okay, any questions?
I have one from
Yeah.
the previous time. You mentioned, can you go back to the, that here.
Yeah.
You're showing that there is a region of high density immediately before the shock wavefront,
Okay.
and a uniform density, or relatively lesser density immediately after the shock wavefront.
After this is of course a uniform. Yeah, this is the original background density.
Yeah. So
yeah, that is
that's
unchanged.
uniform, but that density is much lower than the one just before the shock.
Right. Yeah.
So your simulation is confined to just an infinitesimal space before the shock front and after the shock front.
No, so the simulation, of course, initially in the simulation you start with everything static. Okay, and if you excite a few guys, then you keep track of all the guys which are excited. So these outside guys are not excited, so you don't care. But soon they will get excited, so you can see it's growing, right?
So that initial condition you give in the form of you showed in the Gaussian.
Okay,
The
so
Gaussian energy.
yeah, so the Gaussian is of course like if you look at the overall profile, but at an microscopic level, you just take a few particles and give them some kinetic energy.
Just
Randomly, right? Yeah.
For equal mass case, it is completely integrable.
Equal mass case, it's completely integrable, right? Yeah. So I mean, see this. So you have a set of particles with let's say momentum P1, P2, P3, and you can see that if you, for example, total momentum is obviously conserved, total Pi square is conserved, but even Pi cube is conserved. Right? Because every time there is a collision, they just exchange, right? So everything is so any power of Pi to the power n. So you can find n constants of motion. But as soon as you make masses different, you cannot find any other constants of motion. There are only two constants of motion: total momentum and energy. I just write what happens when two particles with velocity vi and vi plus 1 they collide. After collision, these are the new velocities. Okay. So this just follows from energy and momentum conservation. Okay, so then what we start with is initially everything is at rest, but then we just take a few particles, let's say 4 particles here, and just give them some random energy. Okay. So at a constant level, it's basically, I mean, so the initial condition actually doesn't matter too much, but so anything which is like localized around some center is okay. Okay, and then you just do your molecular dynamics simulation and see what happens. And okay, so this is a picture of a space-time picture of the trajectories of the particle. So this is time and this is space. So at t equal to 0, these particles are excited. Then you can see that at some point some particle here starts getting excited, then at here some particle gets at this time particle here gets excited and then it follows. So here this is the trajectory of a given particle. Okay. These particles are all at rest. I mean till some time and then it starts moving. Okay. So this is the overall profile of the sort of excited particles. And here this dashed line that I have drawn here is this line t to the power 2/3. Okay, so right at the beginning I said that r of t, the radius of the shock front, there is an exact formula, right? Some e by rho infinity t to the power 2/3, and then there is something 1/3, and then there is some constant a, which is also known exactly. Okay, so this is some dimensionless constant. So this curve r goes as t to the power 2/3 is this dashed line. Okay. So you can see that what I see in the molecular dynamics is very close to what I got from that very heuristic argument r of the size.
So that is it possible that your outcome is heavily dependent on the initial condition, energy initial condition?
No, that's what I said. It like any energy you start with. So of course this will change.
Have you tested this with multiple different energy profiles?
No, initial energy we have tried various energy profiles like flat energy profile, Gaussian energy profile, and initial at short times you can see where it's very different. But as soon as you go to large times, it's exact. I mean, you forget all the initial conditions. Okay, so now given, so this is the procedure I mentioned earlier of going from the microscopic to macroscopic profiles. So you just take your simulation data and construct these coarse-grained fields, right? These three fields, and you just plot them. Okay. So these are kind of heat maps of showing how these three fields evolve. So if you look at the density, what you find is just near the shock front it's maximum. At the center it's very low density. At the shock front it's maximum. Okay, so this is kind of wrong what I drew here. It should have been the other way. So at the center the density is kind of less, and then at the edges it's maximum. So it's more like this. Okay, so this is the density and this is the temperature. So temperature again with time you can see how it's changing, and the temperature actually at the center it's very hot. Okay, and then outside there is some profile. So this is it's a heat maps, but we can plot them just as a function of x at different times.
So this heat map for integrable system, how it looks.
Okay, so for if you so integral systems, for example, equal mass case, right? So there the first big difference would be that the scaling, this t to the power 2/3, it would be just ballistic scaling. Okay, so it would just go completely ballistic, and the scaling functions also will be very different. Okay, yeah, so they will have instead of this. So here I said for the rho is some function of x by t to the power 2/3 for this non-integral case. For the integrable case, it will be some function of x by t. So everything scales ballistic scaling.
How could this only case? Sound
So you are saying how do I look at the sound waves in this case? So sound, of course, I mean, if you from here one can find the pressure, and that should have information about the sound, but I don't know exactly where the sound is like maximum or. But because you have to look at the pressure, that should probably tell us. Yes, the sound.
I have one thing. Underneath the sound thing. Can't you just find a continuity relation between the pressure, volume, and temperature before the shock front and after the shock front, and find whether it's the blast is supersonic or subsonic?
See, that continuity is actually what I wrote this Rankine-Huguenot boundary condition. That came from a continuity equation for the three fields.
Okay, but that's just for boundary.
At the shock front.
Yeah, that's exactly the shock front. What
Right.
I'm saying is just before, like I'm saying, that infinitesimal space, before the shock front, right after the shock front.
No,
what's the
but
relation between those two fluid profiles there?
yeah, so that actually comes by taking a difference between before and after that Rankine-Huguenot boundary condition. function,
Okay.
which comes exactly from just using that. Okay, so this is what this again the same thing. The three fields look at different instants of time. Okay, so this is at an early time. At the center, density is low. At the edge, density is very high, and this is the distance r, which is increasing as with time. And this is at the latest time. You can see again there's a sharp discontinuity, high density here, low density at the center. Okay. So this is the density, velocity, and temperature. Temperature you can see it's very hot at the center, and at the edge it has some profile. Okay, so now these are the direct solutions that we get from the molecular dynamics, and now we want to test whether this scaling solution works or not. Right? This expected. So then what you do is you try to collapse this. So if the scaling works, means you should get data collapse. Okay. So you scale x by e to the power 2/3, that is this variable z, and you scale velocity in some way. And then if you plot all these curves, you find that you get complete data collapse. Okay. So this is what one understands by self-similarity and scaling. That you have some complicated behavior at different times, but all the data collapses on doing some scaling. Okay, and then on these plots, I have also plotted the exact solution that I talked about, this TVNS solution. That you can see, there's a dashed line here, which is the exact TVNS solution. Okay, so so you can see the agreement between the TVNS solution and molecular dynamics is almost perfect. Okay, so there are some differences at the for example here you can see a clear difference. The TVNS solution actually has a divergence at the origin, but the molecular dynamics has a finite temperature. So there are some differences that you can see in the core region, but mostly it's perfect agreement. Okay, so this is okay, my time is almost up, right? I think I am almost done. Okay, so the main observations are there's almost perfect agreement between simulations and Euler predictions, except in the blast core. And now we have to understand why is there this small difference. Okay. So, I mean, even though it's a small, we have to understand this. And so now we have to go back and ask, when we wrote the hydrodynamic equations, we dropped these terms, right? We are looking at the Euler equations. So now we have to ask, was it okay to drop these terms? I mean, are we justified in neglecting these terms? So to do that, we do a self-consistency check. We take our solutions and compare, let's say, this term and this term. So we just take the ratio of, let's say, this term with one of these terms, and now using our exact solution, if we compute it, what we find is that in fact there is a small region in the near the core of the blast where these terms become important. Okay. So I won't go into the details, but I mean there's some funny powers and all, so there it gets a bit confusing. But
this equation has self-similar solution.
With this, now it becomes very difficult. First of all, you can no longer obtain an exact solution. No one knows, and that scaling. So if you plug in the scaling solution, you find that it's no longer satisfied, and so this is providing some correction to that equation, which is important. The correction is important in the core region. So that is the problem now.
For any special cases, is it possible in the Navier-Stokes equation, integrability of Navier-Stokes equation?
Yeah, Navier-Stokes, of course, like see, even in 3 dimensions, we know like if you have water flowing through a pipe, we can solve and so on. But in this particular situation of this blast problem, for that initial condition, there are no known solutions. I mean,
One question.
yeah.
So you said this is a cold gas, right?
Outside was cold, and
Outside is cold,
inside is the huge release of energy.
Okay, so that is where the temperature gradient comes.
Yeah, but the temperature, of course, inside there will be everywhere there will be some temperature gradient, right? Inside the and at the center you can see its maximum, the gradients. because they somehow it's very hot there, and so that's why there everything is the dissipation terms are more important.
That's the center is very hard. Why did you see this previous molecule simulation that near the boundary front there is particles of higher energy than at the center?
No. In that in the 2D plot.
Yes.
No, but there what we are seeing is just the density, right?
No, not temperature.
You couldn't see the temperature.
Color has nothing.
No. Yeah, it's just. Okay. So yeah. So now it turns out actually that what is this? Okay. Yeah.
Energy dissipation is very important.
Energy dissipation is important, especially near the core. That is the conclusion. Right. So now next what we did is this of course we can't solve exactly, but we can solve it just by numerical solution. Right? Some partial differential equations, we just solve them numerically. So we solved this full thing again with the same initial condition, and then again we compared with simulation. So here I show comparison of microscopic simulation with Navier-Stokes and also the earlier TDNS exact spinning solution. So let's just look at one of these curves. The dashed line is the TDNS exact solution which has a problem of divergence. This blue curve is the Navier-Stokes equation solved numerically, and this red curve is the microscopic simulation. So we see that if you solve these equations with dissipation terms, then at least it's better than this. You will get rid of the divergence, but you still don't get complete agreement with simulations. So that is one still open problem. Okay, so now, so your question was like, can you still solve the? So what we could do is actually, if you try a different scaling form instead of this some other scaling form, then it turns out that in this equation, if you just make a scaling ansatz and plug it in here, then these terms remain, but some other terms drop off. Okay, and then you can again solve it, and you get a different scaling solution. Now, if you take that scaling solution, you find that it works in the core region, but it does not work outside. Okay. So, I mean, this is what we show here, but again, I won't discuss. Okay, this is also important. Okay, so let me just conclude. So what I try to talk about is there are two descriptions of air in this room: atomistic description due to Newton and the continuum description due to all these people. And our question is basically this continuum or hydrodynamic description, is it always valid? In some extreme situation, can it break down? And we tested this for the evolution of this blast wave in 1 dimensions, where we have an exact solution of the Euler equations. And we find very good agreement with simulations, almost perfect agreement, except for some core region where we have some problem. And so there are some difficulties in getting this complete agreement, because in this equation, if we want to solve this, we have to know what this thermal conductivity and viscosity are. Right? But this also is not known very accurately. So that is one problem in getting a complete agreement with numerics. So there are some very recent work by this IMSC group about results in higher dimension. They have done even more extensive simulations, and now it's very clear that hydrodynamics and microscopics do not match. So this is a very, I think, important open problem. Okay, so maybe I'll stop here, and any other questions?
I have a question.
Yeah.
In model, the masses are like alternately different masses.
Right. Yeah.
What do we have random masses? Like they're not
Okay.
alternate.
Yeah. So if you take random, things won't matter much, but it will become. So it won't help in what we want to look at. So in the sense that if you take random masses, let's say M1 and M2, but randomly placed, right? That's what you want to do. So it's possible that you'll get sequences of M1, let's say. right? And then maybe there's one M2 and then M2 and then M1, M2 and maybe another M2, M2. Okay, so there will be sequences of continuous M1 and continuous M2. Now, these regions of many M1s consecutive will be like, they're kind of integrable. Okay, so it will in effect, it will reduce the non-integrability. Okay, so it won't, it will still work. I mean, it will do whatever, but it won't help in any way. Because we want a model which is far from integrable. Okay, but this will get slightly close. It's still integrable, but it's, as you can see, because there is this continuous, some big regions, and there might be
Some
some
of the regions will be becoming.
close to integrable. Of course, at the boundary, it again meets the M2, so it will not be exactly. But if you have a long sequence inside, it will be look very integrable.
But wouldn't this be more close to reality?
Reality, I mean, of course, like, see, first of all, 1D is a very artificial example. So it's not anyway very real. I mean, the idea is that it's the simplest model where you can do things accurately. So that is the main idea. Right? So, but reality, of course, I mean, yeah.
So we're making it more ideal to it's being non-integrable.
Yeah, in the, as non-integral as possible.
What are the prospects of doing this blast wave simulation in magnetohydrodynamics?
In
plasmas, for example.
okay, right. In the right, yeah.
I think one would be like a typical star supernova itself because it's plasma, it's charged particles in there.
Right, yeah.
We include magnetic fields.
Yeah. No, I think it will be a very interesting question. Like, first of all, even solving the Euler equations and asking what are the, like, are there self-similar solutions and what do they give? And then, of course, comparing with simulations, that will be much more difficult. But I don't even know if it's done or like if like that. But yeah, that would be, of course.
Does this paper by Kumar and Ramesh, does it like say that in 2 dimensions or more, this kind of description is not good?
Yeah, that is the main conclusion. So, what is predicted by the theory? So, in our case, we saw at least, except that a small pore region, everywhere it works perfectly. But in 2 and 3 dimensions, what they find is there's a bigger disagreement everywhere.
Okay.
So, even outside the pore region, it doesn't work.
So what kind of description can like, fit to such cases?
Okay, so let me qualify again. So what they find actually is if you include these terms, then there is better agreement between hydrodynamics and here. Without these terms, there's like complete disagreement. Okay. So basically, then the difficulty is really because if you include these terms, then there are these 2 scaling regimes, the core and the bulk. Okay, and somehow you have to obtain a solution which has both these properties. Okay. So, so that is a technical difficulty. But in some sense, this full equations is probably correct. It's only that the Euler equation which they had used to understand the bond, that is not completely correct. So you have to, the distribution terms are really important.
In 2D, the equations are symmetric extension.
2D, yeah. So 2D basically the, I mean, this will just
Symmetric extension. Symmetric extension of those terms. Rho by rho by, you have.
Yeah. So you have
That is exactly replicative of this term.
more or less, right? Yeah, del x square. I mean, so it's in 3D. It's this is the viscosity term, right? Nu del square d. So it's just you replace it by Laplacian. But the other term, so I mean, this last problem because it has radial symmetry. So no radial symmetry. So you can write everything in using just R. So it effectively becomes a one-dimensional problem actually in any dimension. So that has a simplicity. So finally, it's more or less one-dimensional equation, but slightly changed from this. and
I think we can find solutions, but those may not be physically relevant.
yeah.
We can find solutions.
Yeah, if you can, you and people here should be
It may
able to
not be
find some
physically,
solution.
you can easily throw away.
Okay, yeah. So that for the same kind of scaling solution, if you can find, that will be really
Other
good.
solution, but, we can easily throw away. It may not be useful.
It may not be useful, right? Yeah, to find a physically relevant solution might be a bit difficult. Right?
Coming back to that Twitter, the Kumar and Rajesh paper,
Ah.
dimensions. How do they test it with what kind of physical result they test it with? The equations.
No, so they can did both. So they do the microscopic simulations, and then they solve these full equations
So the disagreement was between the microscopic simulations and the TVNS.
and the TVNS solution, right?
Not
Yeah.
with the physical,
No, what do you mean physical?
like an actual blast wave data or something.
No, not with real experimental
The
data.
problem could also be with the accuracy of the microscopic simulation. Like if there is
Yeah. So the various. I mean, one question is like, are the microscopic simulations done for sufficiently long time, and accuracy? I think they would be very accurate because of this event-driven thing. But the only question is like, because these are long-time solutions, right? So you have to know, did they do it for long? But so that's why they have been doing this for maybe like almost 5-6 years now, and they've been improving their simulations, and still it looks like it's quite convincing that there is a serious disagreement.
the problem is with the modeling using the TVNS.
With the TVN. So I think the Navier-Stokes is probably still correct.
Okay, but the
But
energy one.
yeah. So you can't drop this term. That neglecting this is seriously wrong. That is the main.
Questions from students?
So one small question regarding the collisions we discussed. The result of simulation will it be same for both elastic as well as non-elastic collision, or we restrict ourselves to any particular kind of collision?
No, yeah. If it is elastic, it will be very different. I mean, so yes. So actually, I think this first paper also looked at inelastic collisions. Then, in fact, that formula that I wrote. So I said that this size of the blast goes as t to the power. Huh? But in general, t plus 2. T plus 2. No. Yeah, okay. It's yeah. T plus 2. So this, for example, if you have inelastic collisions like granular material, then this power changes. So I don't remember, but I think it becomes slower, maybe 1/t plus 2 or something like that. And of course, hydrodynamics of granular material, if you have inelastic, that is also an unsolved problem. How to write hydrodynamic equations accurately if you have so what you are asking is when they collide, they dissipate here. Yeah, that is much more complicated. But there are even Rajesh and all, they have also studied this problem with dissipation. Yeah.
Why TVNS solution is not
Granular blast. Yeah, so first of all, granular blast, even the hydrodynamic equations, it's not known. I mean, people see these equations will change a bit, right? So these equations are written for particles which conserve energy. So if you have energy non-conservation, then you'll have some additional terms here. Okay, the loss of energy. So if you include those, then of course it's a very different system. And there, I mean, the TVNS solution is not valid. Of course, you can ask whether there's a similar solution or not. I don't think there is a similar solution in that case.
What is the numerical method you use for solving these
For solving?
the TVNS equations?
So TVNS, of course, was exact. But the Navier-Stokes solution is by some method called
I might be wrong, something like this. Macron.
That's for, especially specifically for Navier-Stokes equations.
it was first proposed for Navier-Stokes. I mean, right in Macron.
This is description of the shock front evolving related to the Kuromoto-Shimizu's equation.
Related to?
The Kuromoto-Shimizu's equation, which describes the evolution of flame front.
No, I think there, because there probably the front has some form, right? Shape. It has a shape and it has satisfies some equation. But here the front is very sharp and it doesn't broaden. Right, yeah. So
This has a more abrupt.
yeah, it is really sharp, right? Yeah. Usually, of course, fronts, I mean, they have some profile and they evolve, right? Yeah, this doesn't.
In particle collider will follow the same pattern as in the microscope. In particle collider, particles scatter in the same way we do in the microscope.
You're saying particle collider?
Particle collider has the satisfied, as we say, neutron colliding an atom like that is.
I'm not sure I understand your question. Can you say again?
If we bombard in the high energy, highly mass particle, the highly mass particle is something like neutron, it follows the same.
Oh, okay. When we are seeing like this Rutherford experiment, like atom is there and you collide with some neutron or whatever. No, that of course is a much more complicated process, right? Because I mean, neutron goes and it gets scattered and something happens. Because there is some interaction between the neutron and the atom, right? But here we are just assuming they are like hard spheres. It's a much simpler model. Hard spheres, like you just take two hard spheres and when they collide, what happens? Okay, so we don't care about like because there is some 1/r interaction and so on, and you have to solve that complicated problem, right? But here there is no interaction till they collide, so it's a much simpler model, right? They completely move straight line until they collide, and then they just it's like carom ball. I mean carom or billiard balls, right? They just completely elastic.
Are there more questions? Not, I'm happy to see that there are questions from students as well this time. So let's wind up this session by thanking Professor Abhishek by accepting our invitation and giving a very illuminating talk. You can wait 5 minutes.
Okay. Yeah.